Prevention and control of fracture in metal structures. In this course, we will learn how to use the basic principles of fracture mechanics to evaluate and control cracks in structures. We will learn about different fracture criteria and how these criteria are implemented in fracture control plan for a specific structure. Let me start first with a summary of the cracking problem in structures. Cracks can be due to corrosion or fatigue. Corrosion is the gradual destruction of materials by chemical or electrochemical reactions with their environment. Fatigue cracks are basically small flaws existing in metal due to imperfections in fabrication. They grow under cyclic loading such as wind and live loads. Under the effect of surface loads, we will have stress corrosion cracking. So basically, corrosion will develop to be a stress corrosion cracking, wherein crack growth is going to be assisted by the effect of the environment. Similarly, fatigue cracks will grow further with the assistance of the environment. The crack growth process will extend to a size that cannot be tolerated by the fracture toughness of the material, and brittle fracture will occur under stress levels that may be lower than the design stresses. This may cause a structural failure. Let me start with material properties related to crack propagation. There are two possible failure modes for metals: ductile failure and brittle failure. This classification is based on the ability of a material to experience plastic deformation. As a general comparison between ductile failure and brittle failure, for ductile failure, we note significant plastic deformation and necking. There's necking and significant plastic deformation that can be recognized from the stress-strain relationship of the material. This plastic deformation is usually associated with high energy absorption before fracture occurs. On the other hand, brittle fracture is characterized by little energy absorption. In this case, there is no elongation and there is no reduction in area. The ductile fracture process is characterized, as I mentioned, by large plastic deformation ahead of the crack. The crack in this case is stable, and stable here means that the crack will resist further extension unless the applied load is increased. Of course, there is evidence of considerable deformation at the fracture surface, such as twisting and tearing. As I mentioned, this kind of failure is characterized by high energy absorption before fracture. If we go through the steps of failure, first, necking begins. Next, small cavities, microvoids, will form in the interior of the cross section. under proceeding with loading and deformation, cavities will expand and merge together to form an elliptical crack. The crack will continue to grow in a direction parallel to its major axis, and then finally fracture develops by the rapid propagation of the crack around the outer perimeter of the neck by shear deformations. The brittle fracture process is characterized by an unstable crack. Unstable crack means that the crack will propagate very rapidly without any increase in the applied stress. There is here relatively little plastic deformation, or maybe there is no plastic deformation at all. The direction of the crack motion is basically perpendicular to the direction of the applied tensile stress. If this is the direction of the applied tensile stress, this is the direction of fracture, perpendicular to it. Now we would like to define toughness of the material. Toughness of the material is the ability of a smooth element to absorb energy, usually when loaded slowly. The units of toughness are inch, pound force per cubic inch. And it can be characterized by the area under stress-strain relationship of the material. This figure is showing several stress-strain relationships of different kinds of steel: low carbon steel, medium carbon steel, high carbon steel. And we can recognize between three different properties of the material. In terms of strength, the high carbon steel is the strongest material. In terms of toughness, the medium carbon steel is the toughest material. And in terms of ductility, the low carbon steel is basically the most ductile. Now, notch toughness is another property of the material, which is very significant while we are using the principles of fracture mechanics. In fact, it is very difficult to fabricate large welded structures without introducing some kind of imperfection in the form of a notch or flaw or discontinuity. The type of flaws that can occur in steel welded detail are basically lack of fusion, porosity, inclusion, undercut or toe crack, in fact, the Sharpe V notch impact test is widely used to evaluate notch toughness. We call this the CVN impact test. Here we prepare a specimen which is in the form of a bar that has a rectangular cross section, and we form some kind of notch in the bar. The bar after that is placed inside the machine. The machine has a pendulum provided with a hammer. We raise the pendulum to a certain height h and then release it. The hammer is going to strike the specimen and fracture it, and then it will swing to the other side to another height h prime. Basically, the energy absorption is computed from the difference between h and h prime and is a measure of the impact energy. Another property of the material is the ductile-to-brittle transition. And one of the primary functions of the CVN test is to determine whether a material experiences a ductile-to-brittle transition with changing the temperature. And this figure in particular shows typical CVN results for common structural materials, which shows the transition from brittle to ductile behavior under condition of impact loading. The CVN impact values at the lower left of the figure are representative of low levels of notch toughness or brittle behavior. The values in the upper right, these are high values for notch toughness and are representative of ductile type behavior of the material. Some materials, such as aluminum and very high strength steel, do not exhibit a distinct transition behavior. Some materials, such as 75 KSI yield aluminum, they have low notch toughness at all temperatures. On the other hand, some other materials, such as high strength steel 180 KSI, they exhibit high notch toughness at all temperatures. After this introduction, we would like to go through the core of this course, evaluation of crack growth using principles of fracture mechanics. Now, we would like to define what is fracture mechanics. Fracture mechanics is an approach to evaluate the fracture behavior of structural members characterized by pre-existing flaws or notches. The approach is theoretical. It is based on stress analysis in the vicinity of the notch. And in order to use this approach, there are basically three types of information that needs to be available to us in order to use the principles of fracture mechanics. First, the fracture toughness of the material as obtained from fracture mechanics tests, and we'll go through all these tests later during this presentation. The applied stress on the structural member being analyzed, and of course the flaw size and geometry orientation of the structural member. In fact, using fracture mechanics, engineers can establish allowable stress level and inspection requirements to design against the occurrence of fracture in structures. Now, what are the basic fracture modes? There are basically three fracture modes. Mode 1 is opening or tensile mode. Mode 2 is sliding mode. Mode 3 is tearing mode. Since we are dealing with isotropic materials, brittle fracture fracture usually occurs in mode 1. So in this course we will focus on mode 1. Let me define what is stress concentration. Basically, if you have a plate such as this one, and this plate has some kind of cracks, we may notice amplification of the applied stress at the vicinity of the crack tip. In this area we may notice an amplification of the applied stress. If you look at this figure here, the maximum stress is basically at this location X and X prime, and as you move away from the tip, the maximum stress is going to be decreased until it reach a value of the applied stress sigma. These pre-existing flaws, sometimes we call them stress razors because they amplify the stress. As I mentioned, the maximum stress sigma m occurs at the crack tip and may be approximated by this equation: 2 sigma multiplied by the square root of A divided by rho t. Sigma here is basically the applied stress. A is half the crack length if you are dealing with a central crack, or equal the crack length if you are dealing with an edge crack. And rho t is basically the radius of curvature of the crack tip. Now, if we divide the maximum stress by the applied stress, we get a value, we call it the stress concentration factor, Kt. So basically Kt equals to sigma m divided by sigma equals to 2 multiplied by the square root of A divided by rho t. However, for sharp cracks, the radius of curvature may tend to be equal to 0. And if you plug this to the equation, so you are going to get infinity. Kt here is going to be 10 to infinity. So basically, based upon this, we can conclude that the stress concentration factor Kt by itself will not provide the whole picture about the stresses in the vicinity of the notch. Consequently, we need to look for another parameter that is based on an analytical method different from the stress concentration approach. So there is a fracture mechanics methodology that can be used for this purpose. Now, the main objective of this methodology is to establish parameters to represent the driving force or the applied stress, and establish parameters to represent the capacity of the crack. If you compare the applied stress to the capacity, we can have some idea if we'll have a brittle fracture or not. This is basically the idea. So basically, we establish parameters for the driving force or applied stress first. And for linear fracture mechanics, we are going to use a parameter called the stress intensity factor, K. This parameter relates the stress field magnitude in the vicinity of a crack tip and the size, shape, and the orientation of the crack. And as I mentioned, since brittle fracture usually occurs in mode 1 for isotropic materials, then we'll further denote K as K1. Calculation of K1 is basically analogous to the stress demand in traditional structure analysis. In traditional structure analysis, we go set structure models for our structures, run the models, and calculate the demand force in each member. So basically, K sub 1 is analogous to this process. Now we need the second parameter to evaluate the capacity, and this parameter is basically a measure of the fracture toughness of the material, and we are going to name it Kc. Now, to prevent brittle fracture, the engineer keeps the calculated applied stress intensity factor K sub 1 below the measured fracture toughness K sub c. Basically, we are trying to compare demand to capacity. There are other parameters such as the J integral and the crack tip opening displacement, or CTOD, are also established for the elastic plastic regime. But we are going to focus mainly in this course on K sub 1, since we are dealing with linear fracture mechanics. Now, in order to define the stress intensity factor, Irwin in 1957 defined this factor using this limit, this equation. And if we consider that the line crack to be like a limiting case or special case of the elliptical hole for the line for the line crack, basically rho is going to be equal to 0, and we have sigma m equals 2 sigma multiplied by square root of a divided by rho. If we take this, plug it into this equation, and consider that rho is equal to 0, so we can very easily come up with this equation. K sub 1 is going to be equal to sigma multiplied by square root of pi multiplied by a. K1 has units of KSI multiplied by square root of inch, or megapascal multiplied by square root meter. So basically, any structure member that has a notch or a flaw, it can be loaded to different levels of K sub 1, but we need all the time to keep K1 less than Kc to prevent fracture. The solution of stress intensity factors for different problems are presented. We are going to present some of them in this course, the most important cases. Basically, we start with the infinite width plate containing a through thickness crack, and this is the equation that we just came up with according to Irwin. Note that this is an infinite width plate, so the plate has here a crack length equals to 2a, and we apply tension stresses to the plate, so K1 is going to be equal to the applied stress multiplied by square root pi multiplied by half the length of the crack. The finite width plate containing a through thickness crack, so now here we have a width of the plate, so we'll use the previous equation, but we will multiply by this function, and this function is basically of a and b. A here is the length of the crack, and b can be representing the length of the width of the plate. It's basically 2a divided by 2b, so a over b. Now, for an infinite width plate containing an edge crack, we have the same equation that Irwin came up with for the central crack, but multiplied by 1.12, and this 1.12 is basically a factor called the free surface correction factor. So basically, if we look at the through thickness crack case that we looked at in the beginning, if we cut it into two, we get the edge crack case, and we note here a 12% increase in the value of the stress intensity factor. If we have a finite width plate containing an edge crack, we are going to use this equation, and again we have to multiply by function of a over b, and note that we are starting with 1.12, the surface correction factor. Similarly, if we have a finite width plate containing a double edge crack, we have basically the same equation, only the polynomial is gonna change, and again note the 1.12 surface correction factor that we mentioned earlier. The next case is an embedded elliptical crack in infinite plate. So basically we use this equation. In the equation, K1 corresponds to the value of the stress intensity factor for a point on the perimeter of the ellipse, actually. And the location, of course, is going to be defined by this angle beta. Q is another parameter. We call it a flow shape parameter, which depends on the ratio of the applied stress to the yield stress of the material. We may notice that at beta equals 90, we will reach the maximum value. At beta equals 90, this part of the equation is going to be equal to 1, and we will reach the maximum value. We take an additional case, which is a surface crack in infinite plate. In this case, we have the equation K1 equals to 1.12, so multiply it here by 1.12, because we can consider that this is equivalent to an edge case. So once we have an edge case, we multiply by 1.12. But in this case, the crack is not penetrating through the entire thickness, same as in other cases that we discussed earlier. Since we are assuming an elliptical crack, so we have to use Q in the equation, and since the crack is not penetrating through the entire thickness, we use another parameter for this, which is mk. It is a correction factor to deal with the propagation which is not extended to the full thickness. mk can be determined using this equation, and you can notice that if this value equals to 0.5, mk is going to be equal to 1. If the value equals to 1, mk is going to be equal to 1.6. One more case, which is edge crack in a beam in bending. So now the stresses are not directly tension stresses, these are bending stresses and can be evaluated according to this equation. We can have some cases where there is a combination of loading. There is a combination of tension, for example, and bending. So in this case, we can use the principle of superposition of stress intensity factor. We calculate the stress intensity factor for tension and the stress intensity factor for bending, and then add up them to come up with the stress intensity factor for the entire case. So here, the stress intensity factor for tension can be represented by this equation multiplied by FA of A over B, and we know FA of A over B can be determined based on the polynomial that we showed earlier, and sigma is basically the load divided by the thickness multiplied by the width of the plate. Then the stress intensity factor for the bending moment can be calculated similarly with the bending stresses and another function for bending. Finally, if you add up the two cases, you come up with the total stress intensity factor K1, which can be calculated according to this equation. Now, what are we going to do with the infinite stresses in the vicinity of the crack tip? We have already shown that the elastic stress at the tip of the crack becomes infinitely large as the radius of curvature at the tip goes to 0. So this is basically a sharp crack, and you can expect infinite stresses in the vicinity. Of course, practically we do not deal with infinite stresses But what happens actually? In fact, what happens that upon loading, the crack tip becomes blunted and a region of yielding and plasticity is going to develop. That's region of yielding and plasticity in the vicinity of the crack tip. We call this the plastic zone. The size of this plastic zone, Ry, can be estimated from stress field equation and can be expressed for the plane stress conditions according to this equation and for the plane strain condition according to the second equation. Note that the plastic zone size for the plane strain condition is much less than for the plane stress condition. For the plane stress condition, yielding is more pronounced. And we'll talk about this later when we discuss the constraints. In fact, Irwin argued that the occurrence of plasticity makes the crack behaves as if it is longer than its physical size. So basically Irwin came and said, okay, I will assume that due to plasticity the crack tip is not gonna stop here, it will extend somehow to the center of the circle including the plasticity zone. So basically he suggested that we increase the crack length by 2 Ry. Ry from this side and Ry from the other side. If we adopt Irwin approach, we can come up with an effective value for the stress intensity factor according to this equation. So we have to take the previous equation divided by this value in terms of the applied stress divided by the yield stress squared of the crack. Now, if we plug the ratio of the applied stress to the yield stress 0.75 in the previous equation, and this is basically a reasonable upper limit to the applied nominal stresses in a structure, we can get 18% increase. As you see here, there is an 18% increase in the stress intensity factor. And even if we go very conservatively and assume that the applied stress is equal to the yield stress, so we will get a 40% increase in this case. So in summary, as a first approximation, we can use K1 equal to K1 effective equal the function of applied stress and the crack length and the plastic zone size. This appears to be a reasonable engineering approach even for stresses approaching the yield strength, as we have showed here. Let me go through an example to explain this further. So we have a larger plate containing a 0.2-inch center crack. This plate is subjected to a tensile stress of sigma equals to 30 ksi. We would like to determine the plastic zone size for two types of steel, 80 KSI steel and 40 KSI steel. So basically, since we have a larger plate, we are going to use this equation. And since we have a center crack, so A here is going to be equal to half of the length of the crack. So we plug the numbers here, we get 16.81 KSI multiplied by square root of inch. Now for 80 KSI steel, we have the ratio of sigma to sigma yield is 0.375. So in this case, we can ignore the use of K1 effective, and we can use the equation directly without K1 effective, and we can obtain a value for Ry equal to 0.007 inch, which is very, very small value. Now, for 40 KSI steel, this is more ductile steel, the applied stress is basically 75% of the yield stress. And in this case, we are going to use K1 effective. So we are going to multiply the value that we obtained earlier by 1.18, and this is going to be equal to 19.835 KSI multiplied by square root of inch. Now if you try to calculate the size of the plastic zone using this value, plug it into the equation, you end up with 0.039 inch, the size of the plastic zone. And if you take this value and divide it by 0.2 inch, which is the crack length, you end up with about 20% of the crack size. So basically here the assumption of linear elastic fracture mechanics is violated, as the plastic zone size is quite large compared to the crack size. Therefore, it is more accurate to use the J integral, which will provide more accurate representation of the fracture, because as I mentioned, the J integral can deal with cases of plasticity. So what is J integral? It is basically a way to calculate the strain energy release rate. So basically the strain energy stored in a member is the area under the force displacement diagram. And if we assume that we are working in the linear phase of behavior of the material, so basically U, which is the strain energy, is going to be equal to 0.5 multiplied by P multiplied by delta, and P here is the applied load, delta here is the deformation of the member. Now, under the application of the load, if the crack try to move ahead by a small value dA, of course the stiffness of the member is going to reduce. So this is going to be the new stiffness of the member. And of course, this will result in reducing the strain energy by this amount, du. So du is basically equal to the area of this triangle. And we can view this as due to the movement of the crack, some energy is dissipated or released, and this is the energy that is released. So the strain energy release rate, and we denote it G, is going to be equal to du by d uppercase A. And uppercase A here is the area of the part of the crack that moved, which is basically the thickness multiplied by the length. For linear elastic behavior, the J integral is basically identical to G, and both can be evaluated in terms of the stress intensity factor squared multiplied by 1 minus mu. Mu here is Poisson's ratio squared divided by A. So for linear elastic behavior, it is straightforward. And in finite element approaches, there are some approaches to calculate J1, and from J1 you can get K1 because they are related to each other. For nonlinear behavior, you can calculate directly the J integral. There is no relation with K1 because we know that K1 is a representation for linear elastic fracture mechanics. Similarly, we can define the crack tip opening displacement, CTOD. Professor Wells, actually in 1961, Professor Wells of Queen's University in Ireland proposed this parameter, which is the opening at the crack tip, to be a measure of fracture toughness. This parameter is basically known today as CTOD. And in the linear phase of behavior of the material, CTOD or delta 1 can be related to the stress intensity factor with this equation. Of course, because CTOD measurements can be made even when there is considerable plastic flow ahead of a crack, this technique can be used to establish critical design stresses or crack sizes efficiently in the plastic regime too. Okay, this was all about the driving force. Now we need to look for how we are going to estimate the resistance parameters, whether they are Kc or Jc or delta C. For linear elastic fracture mechanics, we are concerned with the stress intensity factor. Therefore, we are going to focus here on Kc. Kc can be viewed as a critical value of the stress intensity factor. So Kc here, we can view it as a critical value of the stress intensity factor once you approach this value, you can expect immediately unstable crack growth will occur for your member. Of course, this can be evaluated using lab experiments. So we can define the fracture toughness Kc as the resistance to the propagation of a crack in a structural member. Now, fracture toughness of a material or resistance can vary between linear elastic with no ductility, elastic plastic with limited ductility, and general yielding with considerable ductility. So what are the factors affecting fracture toughness? First, we would like to look at the temperature. And this is a relationship between the fracture toughness and the temperature. As you see, at higher temperatures, the fracture toughness is very, very large. And this is, as I mentioned earlier, corresponds to a ductile mode of fracture. Now, as the temperature go down, Kc drops tremendously, and you're gonna get in this area brittle mode of fracture. So we can say that as the temperature increases, fracture toughness increases. Another parameter which is very important and affect the fracture toughness is the loading rate. The loading rate is expressed in terms of the strain rate inch per second, and these are the limits for slow loading, intermediate loading, and dynamic loading. So from this figure we can expect that under slow loading the maximum can be reached at 10 seconds or more. For intermediate loading, the maximum load can be reached around 1 second. And for impact or dynamic loading, the maximum load can be reached in 1/1000 of a second. So we need to discriminate between these three load rating cases. This figure shows that at constant temperature, fracture toughness tests conducted at higher load rates generally result in lower fracture toughness. So accordingly, we can say that fracture toughness of structural materials increases with decreasing loading rate. Now, let's take a look at the combined effect of loading rate and temperature. This figure shows representative fracture test results for a 50 KSI yield strength structural steel, which was tested at 3 loading rates: dynamic, intermediate, and slow over a range of temperatures. Based on this figure, we can conclude that the temperatures at which the fracture toughness levels begin to increase significantly depend on the loading rate. So basically, this temperature for static, it's around minus 190. For intermediate load rating, it's around minus 125 Fahrenheit. For dynamic, it's around 25, which is very, very significant. Now, constraint is very, very important, and one of the very effective parameters that affect the fracture toughness of the material. Let me first take the case where we test the material in the lab. We always test the material in the lab under uniaxial loading. In this case, only sigma 1 is present. Sigma 2 and sigma 3 are both equal 0, and we determine the mechanical properties according to this test. And as you see, Mohr circle here has a radius. The radius is basically equal to the maximum shear, which in this case is going to be equal to the yield stress divided by 2. So basically, under uniaxial tension test, we can clearly reach the yielding behavior of the material. Unfortunately, in physical scenario, the material is under triaxial state of stresses. Sigma 2 and sigma 3 are present. They cannot be ignored, and in some cases, sigma 2 and sigma 3, under some conditions of loading, sigma 2 and sigma 3 may increase and be close to the value of sigma 1. So if these three values are very close to each other, we'll see that the Mohr circle is going to be very, very small or may diminish. Because of this triaxial state of stress, the principal stresses will approach the ultimate stress and fracture occurs. However, yielding, which is going to be prevented because tau maximum is very, very low, will never occur. So in this case, you may reach fracture without yielding. And this triaxiality of stresses phenomenon is more pronounced in thick plates with notches, as we can see here. That's a plate with a notch, and this is basically the state of stresses. We apply tension, so we have sigma y increase, but sigma x and sigma z both increase too. And accordingly, the mean stress inside this cylinder and this cylinder actually is representing the plastic zone. The mean stress will increase dramatically because of the increase of sigma x, sigma z, plus sigma y. This triaxial state of stresses will restrain the extension of this plastic zone. The plastic zone cannot expand more. It's going to be restrained, and this is why we call that's a constraint. And brittle failure will occur due to triaxiality of stresses. So we can say that as the thickness is increased, the constraint increases, and the stress strain curve is going to be raised. So this is the case of constraint case, but will have limited ductility, of course. Also, fracture toughness of structural materials increases with decreasing constraint. So based on these three parameters, we can come to a very, very significant conclusion. Under conditions of low temperature, rapid loading, or high constraint, ductile materials may not exhibit any deformations before fracture. So under these conditions, even ductile material will exhibit a brittle behavior. So they will behave same as brittle materials. Let me now go through the fracture toughness testing setup. We will further name KC, we'll name it K1C, because all the fracture toughness tests are done under the conditions of fracture mode 1 and under conditions of maximum constraint or plane strain conditions. The two most common specimens used are the 3-point bend specimen, and the compact tension specimen. This is the compact tension specimen. And in order to calculate a maximum value for K1C or KGC, they are expressed in terms of the yield stress of the material and the thickness of the specimen, according to these two equations. Now, let me go through the ASTM standard fracture tests. I'm not going actually to go through the test, but I will outline the title of the test and what you get from the test, and you can go to ASTM standards by yourself and read more about the detail of the test. So the first standard is ASTM test method E-399, standard test method for plane strain fracture toughness of metallic materials. This test is specifically for the determination of K1C. The test is done under plane strain condition, and fracture to be achieved is sudden, resulting in unstable brittle fracture with little or no deformation. Again, when I mention plane strain refers to conditions of maximum constraint, which We are talking here about thick plates and deep cracks. The second test is basically ASTM method E-399 Annex A7, special requirements for rapid load plan, strain fracture toughness, K1C of T testing. And T here is basically representing intermediate loading rates. So T is about 1 second. The time to the maximum load is about 1 second. So this is to determine K1C. So this is dynamic under intermediate loading. Again here, constraint is maximum and failure is sudden, resulting in unstable brittle fracture with little or no deformation. The next test is ASTM test method E-1221 standard test method for determining plan strain, crack, arrest fracture toughness, K1A of ferritic steels. K1A sometimes is referred to as the crack arrest toughness. It is either K1A or K1D. Ferritic steel is basically one type of stainless steel that has a low carbon content, and it has it possesses good ductility resistance and stress corrosion cracking. So this test is basically to calculate K1A for ferritic steel, and this is done under dynamic or impact loading in rapid unstable brittle fracture. The next test is ASTM test method E-813 standard test method for J1C, a measure of fracture toughness, and this test is basically for the determination of J1C. And here J1C is a measure of the fracture toughness at the onset of slow stable crack extension, which means we are running this test under the plastic regime of the material. So the behavior is non-linear elastic plastic. The next test is ASTM test method E-1737 standard test method for J integral characterization of fracture toughness. That's a new test method to develop all J integral test results such as JC, J1C in one standard. Again, the behavior here would be elastic plastic with or without stable crack extension. The next test is ASTM test method E-1820-96, a standard test method for measurement of fracture toughness. And this test can be used for the determination of K, J, CT, OD, or delta. And this test is basically developed for some materials where the type of behavior is not clear, is not known in advance. So the type of test needed is not known. This table shows some values that were obtained for the critical stress intensity factor, fracture toughness K1C. In the first column we have the material name. So we have here several alloys of steel, stainless steel, aluminum alloys, and titanium alloys. In the second column, the ultimate stress of the material is listed. In the third column, the yield stress of the material is listed. And in the fourth column, the fracture toughness obtained during the test is listed. And this column is basically listing the minimum values of the thickness of the specimens used to develop K1C. Let me now go through different criteria for fracture mechanics based design. A fracture criterion actually determines how much fracture toughness is required for a particular structure application. So this is basically what is meant by a fracture criterion. These fracture criteria are usually related to three levels of fracture: plane strain, elastic plastic, and plastic, fully plastic. As you see, for a static loading, the transition region occurs at lower temperatures than for impact loading, for example. And this is basically depending on the yield strength of the steel. Therefore, for structure subjected to static loading, the static transition curve should be used to predict the level of the performance at the service temperature. For structures subjected to impact or dynamic rates of loading, the impact transition curve should be used to predict the level of performance, and again at the service temperature. For intermediate loading rates, we have to use the curve in the middle. The most used fracture criterion is the 15 foot-pound CVN impact criterion. It is even established before the ASTM standards for fracture toughness were established actually. And it was originally established for large welded ship hull structures, and later it was adopted for other applications. It assumes that brittle fracture will never occur if the material of the member has a sharp V-notch impact energy more than 15 foot-pound in the operating temperature. So simply it is based on one parameter. That transition temperature criterion adds another parameter to this parameter. So in addition to the sharp V notch impact energy parameter, it also adds that transition temperature to specify the level of the performance. So this is basically based in two parameters rather than one. For example, you can see here that for the level of performances, we have basically, as I mentioned, three levels of performance: plane strain, elastic plastic, and plastic. We have three types of steels here. Steel 1 will perform at the surface temperature in a plane strain manner. Steel 2 will have elastic plastic performance, and steel 3 will have plastic performance. Another example, basically, let's say we selected our V-notch criterion to be 30 foot-pound. So we have here three types of steel: CS, CN, and B. We can draw a horizontal line at this value of 30 foot-pound CPN. It will intersect with the curve of each element. So basically, the first one, which is CS, we will note that it can be used at surface temperatures as low as -95. However, for CN, they can be used at surface temperatures as low as -30, and the B grade basically can be used at temperatures at about +15 Fahrenheit. The next criterion is through thickness yielding criterion. It is based on two observations that we went through. The first one is that increasing the design stress in a particular application results in more stored energy in structure. We know that the stress intensity factor, which is basically a measure of energy, is expressed in terms of the applied stress in addition to the size of the crack. So basically, as we increase the applied stress, we get more stored energy. The second observation is increasing the plate thickness promotes plane strain behavior. And according to this second observation, one can expect that a higher level of fracture toughness is required to obtain the same level of performance in thick plates as would be obtained in thin plates. And in general, as the plate thickness get decreased, the state of stress, it changes from plane strain to plane stress. So this criterion requires that in the presence of a large sharp crack in a large plate, through thickness yielding should occur before fracture. So basically, this criterion is calling for plane stress condition. In plane stress condition, we can expect yielding before fracture. So for through thickness yielding to occur in the presence of a large sharp crack in a larger plate plane stress conditions are required, and we have to satisfy this equation. So the fracture toughness should be greater or equal to the yield stress multiplied by square root of the thickness of the plate, and in order to achieve plane stress conditions, the thickness of the plate should not be more than 2 inches to ensure plane stress behavior or plane stress condition. Now, in the other hand, to ensure plane strain state of stress at the crack tip, we need to satisfy this equation. A, which is the crack length, T is the thickness, both of them must be greater or equal to 2.5 multiplied by the ratio of the fracture toughness to the yield strength of the material squared. The next criterion is leak before break criterion. The leak before break criterion was proposed by Irwin and his associates as a means of estimating the necessary fracture toughness of pressure vessel steels. And the objective here was that the surface crack could grow through the wall and the vessel leaks before any fracture occurs. In other words, the critical crack size at the design stress level of a material meeting this criterion would be greater than the wall thickness of the vessels, so that the mode of failure would be leaking, which can be tolerated actually when compared to fracture. Fracture may lead to entire failure. So the leak before break criterion assumes that a crack of twice the wall thickness in length should be stable at a stress equal to the nominal design stress. This is the leak before break criterion, very conservative. And this figure actually is showing us a spreading of a through crack in a plate, and showing the crack edges position during increasing of the crack size during progress of propagation of the crack. And these are represented by these contour lines 1, 2, and 3. 3 is basically the critical. Therefore, in order to satisfy this criterion, we have to satisfy this equation. And at fracture, we assume always that the stress intensity factor equal to the fracture toughness. And since we are dealing basically with K1C, not KC, so we need to run some kind of correction, replace KC with K1C in the equation, and Kc can be expressed in terms of this equation including K1C. Beta is expressed in terms of this equation here. Now if we go and take this equation and that equation, plug them here, we end up with this equation. And in order to solve for K1C, you have to use trial and error actually to solve this equation. Let's go through some examples. The first one is straightforward. Fracture load for a cracked beam under bending. So given to us a beam with a rectangular section 150 millimeter by thickness 25 millimeter. It has a length of 2 meters and is loaded in as simply supported with a concentrated load. There is a notch, and the notch is basically on the tension side opposite to the point of application of the load. So this is basically the case that we just explained, the case of bending. The depth of the notch equals to 15 millimeter, and the material properties of the beam, it has a fracture toughness 77 megapascal square root of meter, and it has a yield stress of 1145 megapascal. And we need to determine whether or not plane strain conditions are satisfied for the beam, and also to determine the fracture load. So in order to determine plane strain conditions, this is the equation. The thickness T and the crack length A should be greater or equal than this equation. We have T equals to 25 millimeter. We have A equals to 15 millimeter. Now we're going to plug K1C, which is 77 megapascal square root of meter, and the yield stress, which is 1145, into this equation. We're going to end up with 11.31. 11.31 is less than both 15 millimeter and 25, so plane strain conditions are satisfied. Just one line. Now in order to look for the load, so we have the case of the stress intensity factor for a beam under bending, and it has an edge crack. So A over B is basically A equals to 15, and B is the height of, or the depth of the beam, equals to 150 millimeter. So we have A over B equals to 0.1. If we plug this ratio into this equation here, we get 1.04. F of A over B equals to 1.04. Now the stress is basically equals to the moment divided by the section modulus, and the section modulus is basically TB squared over 6. The moment is basically PL over 4, so we end up that sigma, which is the stress, equal to 3 over 2 PL divided by B squared T. Now at critical conditions, we have K1C, the stress intensity factor, has to be equal to K1C. So this is going to be equal to sigma multiplied by square root of pi a f of a over b. And if we rearrange this equation, we come up with this equation. So we have sigma is going to be equal to k1c divided by square root of pi a multiplied by 1.04. If we rearrange this equation, we can obtain the fracture load P. So we plug all the values here, we end up with a fracture load equal to almost 66 kilo Newton. So basically, this example is straightforward. The second one is evaluation of the fracture load for a mechanical tool. This is our mechanical tool. The dimensions are given, so this dimension D is 250 millimeter, B here is 60 millimeter, and the thickness of the tool is 25 millimeter. Again, we need to calculate the magnitude of the fracture load if we have a crack length of 5 millimeter. This example actually is going to illustrate to us how can a small notch in a tool can limit its load capabilities. So basically here we have two cases, a case of an eccentric load, so this is gonna cause moment and there is tension, so basically superposition for tension and bending moment. So we have a case of finite width the plate containing an edge crack, and we have a case of edge crack in bending, in beam bending. These are the equations for the first case, and these are the equations for the second case. All are coming from what we presented before. All what is different here is this value, this function for tension is different than for bending. Now for crack length of 5 millimeter, we have A over B equals 5 over 60 equals 0.0833. So we plug this value into the two functions, one for tension, FA is for tension, FB is for bending, so we get 1.163 for tension, 1.047 for bending. And then all what we need is to calculate the stress intensity factor, which is superposition of the two cases, and this equation has been given to you earlier. If you go to the tables, you'll find that the critical fracture toughness factor for this material is 59 megapascal multiplied by square root of meter. So at fracture, this value should be equal to this equation here. So if you plug all the values, if A of B 1.163 plus 6 E over B, B is 60, E here is basically the value of D, which is 250 millimeter. and f of b was calculated as 1.047. Multiply this by the crack length, which is basically 5 millimeter. If you plug all these numbers together, you calculate a value for P equals to 25.8 kilo Newton. The total maximum stress is going to be equal to this value P divided by BT plus 6PE B squared T. This is the tension stress plus the bending stress. If you plug these numbers here into the equation, you end up with a total maximum stress of 447.2 megapascal. Now, if you compare this value actually to the yield stress of this material, which is 1503 megapascal, you find that it is very a lower value. However, because of the presence of the crack, the maximum stresses on this tool were limited to this value actually. So if the stresses exceed 447 megapascal, the tool will fail in a brittle fracture mode. This is what we need to understand, and the example illustrates how the presence of a small notch in a structural element, it can limit its capabilities to sustain loads. The third example, prioritize structural repairs at a site. So here an engineer inspected two structures at a site. One of them is basically a truss that is made up of aluminum tubular sections. Each one has an outside diameter of 4 inches and wall thickness of 0.25 inches. According to his inspection, it was revealed that there is a circumferential through thickness cracks of 0.6 inch length on these members. A recent load rating of the structure showed that these members are currently carrying 47 kips tension loads. The second structure he inspected is a high strength steel pressure vessel that is carrying 5000 psi of internal pressure and has 30-inch nominal diameter and 0.6 inch wall thickness. Inspection of the pressure vessel revealed a surface flow of length 2 inches and an A/2C ratio of 0.25. Now, which structure should be repaired first according to this information? Given here the material properties of the tubular sections and for the high strength steel used for the pressure vessel. 64, 21 yield stress and fracture toughness, 180 and 220 for the yield stress and the fracture toughness for the high strength steel. For the truss structure, that's a case of a plate with a finite width. So the width of the plate 2b is basically equals to pi d, and pi here is basically 3.75 inches from center to center. Why? Because it is mentioned that the outside diameter is 4 inches and the wall thickness is 0.25, so basically the diameter is 3.75, so 2b is going to be equals to 11.775 inches, which means that b is going to be equal half this value. A, half the crack length is 0.3 inches because the crack length is 0.6 inches. A over B is going to be equals to 0.051, and F of A over B is going to be equal to 1.01 as shown by this equation here. Now, this is the equation for the stress intensity factor. So sigma maximum for this case is going to be equal to the fracture toughness for this material divided by this value, and the fracture toughness is 21 divided by this equation is going to give you 21.4 KSI. This is the area of the cross-sectional area of this member, 2.94 inches square. So basically the maximum tension load the member can sustain is sigma A equals to 51.36 kips. Beyond this level, brittle fracture will take place. Therefore, the extent of damage can be expressed in terms of the factor of safety. The factor of safety here is basically the value that the maximum value that this member can take now divided by the value of the load that the member is currently resisting. So we have a factor of safety for member for structure 1 equals to 1.093. Now, for the pressure vessel structure, we have A over 2C equals 2.25. For 2C equals 2 inches, A equals to 0.5 inch. The general relation among K1 sigma and A for surface flow is basically can be obtained using this equation, and again the stress can be equal to the fracture toughness divided by this equation. So basically the maximum stress for the pressure vessel is basically the fracture toughness divided by this equation. Now it is very clear here that Q is function of the design stress or function of the maximum stress. So we have to use some kind of an iterative procedure to solve for this. So we don't know what's Q, so we're going to assume a value of 1.4 first. something here at A over 2C equal 0.25, I'll try to take a value in the middle, so I'm gonna take it equal to 1.4 as a first trial. And MK can be calculated actually directly, equals to 1.396. A over T is given to us. So for the first trial, we are assuming that MK equals to 1.396 and Q equals to 1.4. We calculate the maximum stress. If we plug all these into the equation, equals to 133 KSI. Therefore, the maximum stress equal to PD over 2T. The maximum internal pressure can be calculated as 2T multiplied by sigma maximum divided by D equal to 5,320 PSI. We know that sigma maximum 2 equal to 133 KSI, so now we have a value of 133 divided by 180 equal to 0.74. We need to consult the chart again for Q. We find that Q is basically 1.35. So we started with 1.4, we ended up with 1.35, which means that I need to go through a second iteration. So my second iteration is going to be with MK equal to 1.396 and Q equals to 1.35. If I plug these values into the equation, I end up with a maximum stress equals to 130.5 KSI and a maximum internal pressure equal to 5,220 PSI. Now the ratio of the maximum stress to the yield stress in this case is 0.725. So if I consult the chart, I find that Q is basically 1.36. So I started with 1.35, I ended up with 1.36. I'm gonna run a third iteration with I will start with 1.36. I end up with a maximum stress 130.8 and the internal stress is 5,232 PSI, and the ratio of the maximum stress to the yield stress this time is 0.726. If I consult the chart, I get Q equal to 1.365 and I'm satisfied this time. There is no need of any further iterations. Therefore, the factor of safety against fracture for structure number 2 is going to be equal to this value that I obtained finally, which is 5,232 divided by the internal pressure that this structure is taking right now. So we have a factor of safety of 1.0464. When I compare this factor of safety for structure number 2, I find that the 1.0464 is basically less than the factor of safety of structure number 1, which had 1.093. Therefore, structure number 2 is more critical. Although the flaw is basically a surface flow, is not a through thickness crack flow. When I compare it to the other structure which had a through thickness crack flow, but the numbers is showing me that although it is a surface flow, but the factor of safety here is less than the other one, so therefore structure 2 should be repaired first. So basically this example is giving us, is very significant actually for engineers who run inspection of structures. They can use the same analogy to prioritize their structures for repairs. The last thing I'm gonna go through is fracture control plans. What is a fracture control plan actually? We need to understand that a fracture control plan is a specific set of guidelines, recommendations, and criteria that are usually developed for a particular structure. So you cannot generalize it for all the structures. It's very important that you cannot generalize a fracture control plan for one structure to another structure. Each structure should have its own fracture control plan. These sets of guidelines and recommendations should include, but not limited to, first, knowledge of the surface conditions to which the structure will be subjected. So basically the first step in design is to establish the probable loads and surface conditions through the design life of the structure. And basically during this process we can determine the rate at which these loads are applied, which is very significant because it is going to control the testing method that I'm going to use in order to establish whether I'm going to establish KC or K1C or K1C of T. So whether the load is slow, intermediate, or dynamic. The testing protocol is going to be different actually. For example, for bridge structures we may use intermediate loading, and for machine foundations that are exposed to cyclic dynamic load, we may have actually to use dynamic loading rate actually, not slow loading rate. So it is very significant to look at the surface conditions and the way the load is going to be applied to the structure. Second, the use of structural materials with adequate fracture toughness is very important, because we have already known from this course that the three primary factors that control the vulnerability of a structure to fracture are the tensile stress level, including effects of constraint, residual stresses, stress concentrations, and so forth, the size, shape, and orientation of the crack or the discontinuities in the structure, and the material fracture toughness at a particular temperature, surface temperature, loading rate, and plate thickness. So basically some kind of information about the fracture toughness has to be developed using testing. These guidelines, action, and recommendations should eliminate or minimize stress razors in the design. We know that stress razors in the form of flaws or sharp corners, scratches or notches, all these are able to amplify the applied stress, and if we can avoid them, it would be better for design and for the health of the structure. Control of welding procedures, very significant, because most of the fatigue cracks are basically localized in the welding area due to poor welding procedures. So if we control these welding procedures by testing using some kind of non-destructive testing, ultrasonic testing, all these methods can improve actually the quality of the weld, and we can avoid some kind of imperfections that may exist and can cause some kind of problems in the future. Also, proper inspection plans of the structure is very important. These are very significant to detect any cracks in the early stages and to define some kind of repair measures. This is basically the end of my course. I hope it was interesting. I provided here some of the references that I used in the preparation of this course for your convenience. If you would like to go through these references, it would be good. Thank you very much for your listening, and goodbye.